Welcome back, everybody. I think we're ready to continue. This morning, we had an interesting contrast between the presentations by Sasa and Ming. Sasa talked about the problem on the ground. Ming talked about some of the very real problems of applying AI in an assured and secure way to address problems like this. And you can see the gap, I think, that exists in there. As we go into the last part of this workshop, we're going to be talking about some applications. So I'm glad to welcome Varun Krishna from C3 AI to tell us how to use AI to improve energy efficiency in university campus buildings. So Varun, the stage is yours.
Thank you for the introduction, Costas. I'm going to share my screen. Well, it's really wonderful to be here. Thank you very much for inviting me to give this presentation and also be a part of the panel. I'm Varun Krishna. I'm a manager on the data science team here at C3 AI. So for those of you who are not kind of familiar with C3 AI, I mean, you've seen our name. We're the primary sponsor for DTI. But I'd just like to give a quick introduction of what we do. So C3 AI is the leading enterprise AI software provider for accelerating digital transformation. That's what DTI is all about. We were founded about 11, 12 years ago. Our founder and CEO, Tom Siebel, who you can see in the picture here, is a celebrated industry veteran who invented customer relationship management. Our company went public in December of 2020 under the ticker symbol of AI. And we are hiring data scientists in multiple locations in the United States. So if you or your students are interested in working at C3, then the more academically inclined people would find our data science team very interesting to work with. And we're also hiring across the world in Singapore. I know that we have some colleagues here from Singapore, so we are hiring in Singapore as well, and London, Amsterdam, and Rome. So just a little bit about my path over here. I actually got my undergrad degree in NUS, and I got my graduate degree at the University of Illinois. And so being part of this event is really special to me because I'm sharing a stage with representatives from both NUS and the University of Illinois. So it's great to be here. In fact, on my Ph.D. committee at Illinois, Carl Gunter was one of the members of my committee. So it'll be wonderful to be sharing the panel with him later in this talk. So today I will be presenting the following topics. So I'll talk about some of the AI use cases solved by C3 overall. I'll talk about smart institutions, which has a focus on campus buildings. And then I'll go into a deep dive of one of our AI use cases that are relevant to buildings, and that's our HVAC optimization methodology. It kind of rides on top of Stefano's presentation from yesterday. I'll talk about some results where when we applied that methodology to one campus at the Ohio State University. And then finally, I'll talk about some practical challenges that people from academia will appreciate a lot because I know what it was like to be an academic, and then now that I'm in industry, there are some very interesting practical challenges that I did not face in academia. So I'd be happy to kind of share that with the audience here. So let's talk about C3's use cases from a broader sense. So looking at the screen, there are multiple columns. These are industry verticals like financial services, manufacturing, et cetera. So C3 AI has customers and applications across all of these industry verticals. The horizontal axis, which is the rows here, are the individual applications that we have. So we have reliability, supply chain optimization, fraud detection, et cetera, as you can see on the first column on the left. And today's focus is going to be on energy management. So in October of 2019, C3 partnered with NG to launch an AI-powered energy management solution for large institutions. So this is called Smart Institutions. And most of my talk today is going to be focused on smart institutions. So smart institutions focuses on primarily office buildings, education buildings like university campuses, as well as healthcare. And these are the top consumers of energy in terms of commercial buildings. So that's kind of our focus right now. And of course, there's every chance that once we've knocked off the top four, we may move down the list to other types of commercial buildings. So here are some of the AI use cases that we're solving in smart institutions. The first one is demand forecasting, and this ties very closely to Sasha's presentation from this morning. So I hope people who are in this talk now were also at Sasha's talk, because she gave a very nice overview of how the power grid works. And really, demand forecasting is about the university campus's relationship with the power grid. So what we are trying to do in this use case is save peak demand charges by reducing demand during peak hours. So Sasha also talked about that earlier today, about reducing shedding load. So that's really what this use case is about. There are two types of demand charges. One is levied by the utility, and one is levied by the independent system operator. So that's like the power grid operator in that area. So for example, in the Ohio State University, their utility is AEP, and their ISO is PJM. So the utility operates for the most part on the distribution side of the power grid, and the ISO operates more on the transmission side of the power grid. And if you're a large enough consumer, like a campus building, then you may suffer from these peak demand charges that are levied by both the utility and the ISO. So here, the problem that we're trying to solve is before you hit a peak, you want to know that you're going to likely hit a peak so that you can reduce your demand and reduce the charges that you're going to incur because of that demand. And of course, the benefits of reducing demand are that you will save money, and that's a huge motivating factor for most of industry-related applications. So, but on the other side, as Sasha pointed out, there are several other benefits to reducing energies, and that is a positive impact on reducing carbon emissions. So, in this scenario, when we talk about the utility demand charges, there's one peak per month. So every month we need to be able to forecast when we are likely to hit a peak, and then we need to we send an alert to the facility manager at the campus, and then they will shed load. They'll shed load in a variety of different ways. But we are not our C3 AI system does not perform the actuation part of the process. We do the forecasting, and then we create an alert. And the goal over here is we don't want too many false alerts. So we don't want to be giving alerts every day saying that today is likely to be a peak. So ideally in a month, we flag 3 days at most, or even 2 days, to say that one of these 2 days is likely to be a peak. And so if you reduce your peak, then you'll save money. It's much harder at the ISO level because we're looking at 5 peaks in a year. And so you don't know when the peak is going to happen beforehand. And so we need to kind of, so we have an adaptive forecasting algorithm that will will within 9 alerts or so, at most 9 alerts, we will catch the 5 peaks, and these peaks are determined by an hour. So we need to know which hour in a year is going to be one of the top 5 peaks. So it's quite a challenging problem, but we have been able to solve that successfully. The next area is data cleansing and anomaly detection. So in this topic, we've got issues with bad data, missing data, and so we need to use machine learning to intelligently interpolate that data. And we also throw alerts when certain sensor readings are anomalous. The third use case is chilled water forecasting. And so so chilled water is used for air conditioning. So chilled water is generated at certain centralized plants on the campus, and it's pumped to various different buildings. And we need to kind of forecast the need for chilled water at different buildings so that an energy efficient scheme can be deployed to ensure that chilled water is generated in a way that is that saves energy and costs. The final use case that we've actively deployed, of course, there's several other use cases that we are adding to smart institutions, including solar forecasting, is HVAC optimization, and that will be the topic of today's deep dive. So Stefano yesterday was talking about how there are many groups that are optimizing for energy, and we are one of those groups. So over here, the AI objective is we want to find the optimal temperature set point by finding the value that minimizes the AHU load while respecting comfort constraints. So the AHU load is in the objective function, and the comfort constraints for occupants are constraints in the optimization formulation. So this is a fairly simplistic view of the model. There are several other variables that we could consider, but the most important ones are, of course, the temperature set point that's being set in a building. What are the outside weather conditions at that time? What is the occupancy level, and what is like the historical load? So that's kind of like an autoregressive component. So we can model the load, and then we can also model the comfort associated with that temperature set point. And then we can find the optimal temperature set point. So over here, we are optimizing for reducing energy. So we are not optimizing for maximizing comfort. Comfort is a constraint. And so that in that sense, it's kind of a reverse formulation of what Stefano was discussing yesterday, where really he was trying to find, try to maximize individual comfort. And there were certain situations where that does not necessarily lead to energy savings. But over here, we are optimizing for that energy savings. So let's kind of like dig into some of these models that we're using. So here's a very busy plot, and I'll kind of walk you through it in stages. So as I said earlier, to minimize AHU load while maintaining acceptable comfort levels, we need two models. We need an AHU model, which is the air handler unit, and that is this solid line in the plot. I'm not sure if my cursor is being captured in the screen share, but I hope you can see the solid line. And really that line is answering the question of what is the AHU load for different temperature set points. So if my temperature set point is like 16 degrees Celsius all the way to 32 degrees Celsius, in an air conditioning system, the cooler I set my set point, the more my AHU load is going to be. And the higher I set my set point, the less the AHU load is going to be. So really, we want to find the lowest point on this solid curve that is essentially minimizing energy consumption, right? The second model is the occupant comfort model, and that's this dashed line over here, this bell-shaped curve. And this is a derivative of a standards-based metric that I'll discuss in a second, and that's the percentage persons dissatisfied. So here we're looking at percentage persons satisfied. So in terms of percentage persons satisfied, what we're seeing here is in this particular situation, and there's some assumptions here that I'll be explicit about soon. The maximum satisfaction is somewhere around 25 degrees Celsius. And the satisfaction drops as the temperature set point is decreased beyond a certain point when people start feeling too cold. All the comfort drops when the temperature set point is increased beyond a certain point when people start feeling too warm. So if we were to set a constraint saying that we want at least 90% of people to be satisfied, then we can find the temperature set point that ensures that we will meet that constraint. And so the recommended set point is going to be in the bottom over here, and that will ensure that we are minimizing the AHU load while staying within this range of 24 and 26.7 degrees, which will ensure 90% comfort. So we will recommend a temperature of something like 26.7 degrees for a load shedding event, for example, right? So in this case, if we're kind of informing load shedding by suggesting what temperature set point can be set in a building space that will respect comfort constraints. So this work was published in ACM BuildSys a while ago, and I was a co-author on this paper. And I've noticed that it's a small world. Now, not only have I gone to the universities that people on this panel are associated with, but I've noticed that the ACM BuildSys technical program committee also has several members who have presented at this workshop today and on Tuesday. So it's really a small world, and we publish in the same places and come from the same places. So let's just kind of take a step back. So we were able to model the AHU load. That was the first goal. And so we're going to use machine learning to model that air handler unit load. And we're going to do this for each building. The second goal is to recommend that satisfactory temperature set point. And that set point is going to utilize that AHU load model, so that solid curve. And then finally, we're going to calculate the savings based on actual energy consumption and estimated energy consumption. So I'll be presenting these soon. But first, let's talk about how we do the air handler load modeling. So here we have a standard regressor setup where the air handler unit load is the target, and we would use a room temperature set point. That is our control variable, and so that is one of the inputs. And then we've got environment variables, like we have the external temperature, and that includes a 24 hours ahead forecast. So we have a forecast for the next day, and really what we're doing here is providing a schedule of HVAC temperature set points a day ahead. So we need that day ahead forecast. So we can provide this this actionable schedule that facility managers can then put into practice when they want to shed load, right? So that forecast is important for that reason. And then we also have autoregressive features. It's a forecasting problem after all. So we're forecasting that AHU load, and then we're also going to be looking at building occupancy, and that may be a separate modeling approach as well. In fact, we also had a building occupancy forecasting algorithm in the same paper that I talked about on the previous slide. So there are several different machine learning algorithms that can do this sort of regression, and so we are using the light GBM, but that's really not the crux of what we're trying to do. It's really more the problem formulation than the hammer that we're choosing to use on the nail. As far as comfort-based modeling is concerned, I think Stefano briefly mentioned this. So we are using an ASHRAE standard, ANSI ASHRAE standard 55. So this is a predicted percentage of persons dissatisfied. And then if we kind of take 1 minus that number, or if it's expressed as a percentage, 100 minus that number, then we get the predicted percentage of persons satisfied. Now, the predicted percentage of persons satisfied is dependent on several different factors, right? So it's dependent on the indoor air temperature. It's also dependent on what kind of metabolic activity the occupants are doing, like are they seated? So on the plot on the right, this is for seated occupants. So students in the classroom, they are seated, right? And what are they wearing? So depending on what people are wearing, then so if you are wearing very warm clothes, then you would want the temperature to be a little lower, because if you're wearing a coat inside a room and the temperature is high, then you'll feel more uncomfortable than if you're wearing just a t-shirt and the temperature was high. So the clothing is an important aspect, and the metabolic activity. If you're in a gym, if you're running on a treadmill, then you may want the temperature to be set a little lower, right? So what we're trying to do here is we're trying to set the HVAC set point to ensure a minimum percentage person satisfied of, let's say, 80%. That's just an example, but this is configurable in the application. And so what we find is that when the external temperature is less than 60 Fahrenheit, then we could assume that people would be wearing typical winter clothing. And so the inside temperature that we needed to set to ensure 80% of people are satisfied would be in this range of 57 Fahrenheit to 74 Fahrenheit, right? So we would want to keep the temperature set point within these ranges. And of course, the assumptions are different depending on what the external temperature is and what people are wearing. And we would want to minimize the load within these constraints of what the temperature set point should be to ensure that satisfaction. So just kind of like diving in a little deeply into our deployment at the Ohio State University. So in this project, there are several facilities. There's 485 buildings. We've got 25 million square feet. So it's a huge campus. There's some 18,000 connected devices, and we are expecting to save about 25 to 30% of energy in 10 years. So let's look at an example with Ohio State University and look at how well we're doing with modeling air handling unit load, right? So this is a day ahead air handling unit load, and we're using a symmetric mean absolute percentage error metric. So this is, if you're familiar with mean absolute percentage error, this is symmetrical in the sense that that denominator is not just the actuals, which is what you would have for mean absolute percentage error, but it's the average of the actuals and predictions. So you kind of reduce a couple of risks. One is that this is symmetrical. So you have both predictions and actuals represented in both the denominator and the numerator. And we've got, we also kind of reduce the risk that we're going to be dividing by a small number. And there are many metrics that handle like a division by 0 that could happen, or a very small number that could blow up this metric. So we are using symmetric mean absolute percentage error. And so by using the features that I talked about, the model inputs, we were able to get to like a 3.28% error for this particular building, but that's kind of typical. And I'll talk about some of our metrics for other buildings as well in a second. So now let's talk about the set point optimization, right? So if we were to do a retrospective analysis where we know what the actual consumption was, and which would be like this mustard colored curve in the plot on the right. And then if we were to run our algorithm for the HVAC set point and then model how much the load would be if our set point had been used, then we get this red curve on the right. So what's between these two curves is the estimated energy savings. And that's really what we're kind of going for. Right, and we're also ensuring that our recommended set points are going to be different from the actuals. That's how you save energy, but they're also not too different in the sense that we're not going to have a crazy drop of between the actuals and the set points, because that would again it would come in the way of occupant comfort, and we don't want that. Right. So depending on what time of the year it is, you have different levels of savings, different in terms of both an absolute amount and a relative amount. So just kind of like looking at 3 campus buildings, as I said earlier, Ohio State itself has about 485 campus buildings. So just for 3 campus buildings, our estimated savings using that retrospective approach that I talked about earlier is something in the order of $55,000 for the year. And that alone accounts for an average savings of 19% per building. So this is just for HVAC set point optimization alone. There's several other things that we're doing here at C3, but this is just for this one application. We're already kind of hitting at that 19% point, which is pretty close to our expected savings over a 10-year period overall, which is in the order of 20 to 30%, right? So if you look at three different buildings, some of the buildings have one air handler unit, some of the buildings have three air handler units. So that's kind of a variable thing. And so one of the requirements for our application is we need to know what air handler units are associated with what set point controllers, right? So then we can create that model. And depending on the air handler unit, for some air handler units, the one that I just showed you, we had a very low error for the day ahead forecast for how much load would be consumed. But for other air handler units, the error could be higher, almost like 5 times higher than that, right? So there's a 15% and a 3% on that same row. And depending on the building, depending on the space, the savings could be huge or the savings could be small, right? So in the same building, in building 1, in AHU1, we've got for, like negligible savings, with AHU3, which is in this case servicing like a large library space, right? So in that case, there's a lot more potential for savings when you have these large spaces that are not going to be highly occupied. So now let me kind of try to close off with some challenges that we would face in practice. So the first challenge in practice is the availability of historical weather forecasts. Now, this is important because when you're using weather forecasts as features to your machine learning model, you need historical weather forecasts for training. So if I'm using a 24-hour ahead weather forecast, then I would need to know what my weather forecast was 3 years ago, if that was part of my training set, 24 hours from that day. And the reason for that is there is inaccuracy in the weather forecast, and we want the model to adapt to that inaccuracy. So if we used actual weather data from the past instead of forecast data to train the model, then we find that the model tends to overfit on those features. So it realizes that the weather is a very highly determining factor for what the load is going to be, which is fine, but we want the model to not be too reliant on that feature, because in practice, the forecasts are not that accurate. The next challenge is bad basing data that I talked about earlier. And so we need to kind of intelligently interpolate that data, the missing data. The third one is a very interesting challenge that, again, in academia, we would not think of some of these issues. So anyone who's done forecasting here in the audience would be familiar with the persistence model. The idea of the persistence model is that you forecast that your next period is going to be the value of the current period, right? So you're just kind of persisting that, and that's your persistence model. So if you were to train most autoregressive forecasting models, you would find that if I was to do a 24-hour ahead forecast, then the inputs that matter the most would be the ones that are most recent. So 1 hour ago would have the most predictive power, and maybe 24 hours ago would have the most predictive power. But the issue that we find in practice is that when you've deployed this model, the model is very overfit to some of these features, like what is the most recent hour of measurement. So it takes that sensor reading and it's expecting that to be the best predictor for the future. But sometimes you may not have that value because of delays in data arriving from sensors to your system where you're running the AI model. You may not have the most recent data to make a forecast. And so you may have to potentially take that out of your model or introduce some concepts related to like dropouts. So the model is not overfitting on those most recent features. And of course, there's some practical concerns like inadequate sensorization. So So we need the AHU load to be measured for us to be able to model it. We need to model it so we know what the savings would be if we had not gone with our set point recommendations. And final challenge that we kind of see here is inadequate record keeping. So the set point changes being recorded, right? So we need these. We need a certain level of commitment from the facility side to maintain records. And for example, if they are doing a demand reduction event, it's important for us to know that they're doing that, so we can kind of count that towards the savings that we have had to achieve. So I'm going to pause here for questions. I know that I kind of spoke a little fast. I had a lot to cover, but I wanted to also leave some time for questions.
Thank you so much, Varun, for an excellent presentation. This is a subject near and dear to many people's hearts, including mine, who have done quite a bit of work in forecasting and prediction and control using various techniques, especially in tropical environments where cooling is quite expensive and dehumidification, latent cooling, is perhaps the most expensive of them all. So thermal comfort is really sometimes a constraint, sometimes a co-objective. But I want to ask maybe an unfair question to you. Maybe add a challenge or get your response to that. When the pandemic hit, the building shut down. Okay, so clearly, I'm sure anybody could optimize for a shutdown building and optimize the energy. But then we started reopening and then we started reclosing. So it was not a model that was stationary anymore. One day
Right.
we'll open and then a few weeks later we'll go to 50% occupancy and so on and so forth. How would an approach like this cope with this new reality?
Yeah, no, that's a fantastic question, right? So essentially, the issue that we would face is what we call a regime shift or a change point, which means that your model has been trained on a certain type of distribution of data, and now COVID has hit, and now the model is being used to run inference on a totally different distribution of data. So yeah, I mean, it is a very difficult problem. So in terms of training, so for example, now that we've got our model running in live and the campus has reopened and people are coming back in, what we really need to do is ensure that we have the right features. So for example, let's say occupancy is important.
Sorry, Varun, that message was not meant for you. I didn't mean to go. I put something on the chat that was not meant for you. So please continue your
Okay. Yeah. No worries. Yeah. So if you have some of the right features, then those features should capture the changes in the environment, for lack of a better term. So for example, when the occupancy is low, as you rightly said, it's easy to kind of optimize for that. But now when we have our models running, we have to some extent, mask out certain periods that had a dramatic distribution shift in our training data. So for example, there may be months of data that we will not use in training because we don't want those behaviors that are kind of outliers. So we can't think of COVID as an outlier. And we're going to take that outlier out of our training data. We train on the rest of the data, and that's how we kind of adapt in practice. But it's a tough question, and so these kind of regime shifts keep happening, and so we also have methods to detect regime shifts. So what is the probability that the distribution that I'm seeing right now is very different from what I've been seeing in the past 6 months, right? And that would trigger a retraining. So we may want to retrain on the most recent data and predict in that regime. So that that kind of assumes that the most recent data is going to be most informative for making immediate future predictions. But yeah, these are some of the techniques. And if you have other ideas for dealing with this, please let me know. I'm all ears. I'm also here to learn from other experts who've dealt with this issue. But this is a difficult issue.
Thanks, Varun. All of us are learning all the time with these interactions. I'll be glad to discuss some of our ideas, offline.